Hello everyone and welcome back to another video. Today will be the second video in this long series of our chess engine and explaining exactly how the chess engine works in playing the game of chess. So in this video we'll take a look at all the foundation functions. So if we go back to our mind map, it's basically this top left section, the first one, which covers all the foundation functions. So let's have a quick look at the actual code for all of them. Okay, so we have these three functions, which are vector addition, subtraction, and division. So the reason why we do vector addition, subtraction, and division are internally the way each of the pieces are represented inside the 8x8 array or with a set of coordinates, right? So each piece has a unique set of coordinates which represents where exactly it is. So for example, in the starting arrangement of about if we to just pull up the board right here. Okay, so in this particular position, the e4 pawn, it's basically like on this particular coordinate. However, if we're to represent this with a computer, then we basically represent this entire grid with an 8x8 array. And then this is basically the 0th row, and this is the 0th column. So then this would be the first row, this would be the second row, third row, and fourth row, okay? So if this is the fourth row, and this is the fourth column, okay? So this over here would basically be 4, 4, i.e. being the fourth row and fourth column. Likewise, this would be the second column and the second row. So this would be 2, 2. And likewise, each piece has its own unique position. And for that, we need these three functions. So what these are is, let's say we want to transition from one piece to another. Then we basically need to do the following thing. So let's say we wanted to go from the knight's position to the pawn's position. We want to determine what vector it is from the knight to the pawn. So then we basically perform a vector subtraction there. So what this would do is it takes the second vector and then it subtracts it from the first vector and then returns the output. And similarly, if we want to do the reverse, if we want to see what vector we would need from the pawn to get to the knight, then we would basically do v1 plus v2. Except we also have this scale. So what the scale does is it basically just scales it. So for example, if we were to just play a few more moves here, and if we were... Okay, so this is basically the board once again. For example, for this queen, we can basically move it to this square, or this square, and we have several different squares of which we can move it to. And then all of those squares would basically have, it would be the same vector to transition from any of those squares. However, it would be a different scalar of the vector. So then it would be scaled by a different amount, which is why we have the scale variable as well. So it basically just multiplies the second vector, which is the direction vector, by how much it's scaled by. And it's defaulted to just being 1 if no parameter is passed to it. Oh, I've accidentally made a bit of a typo, but no worries. Okay, so now let's go to the next function. Now we have vector division. So what this does is it basically determines whether one vector is a multiple of another vector. So what does this actually mean? So once again, if we go back to our board, then if we basically play this particular move again, and if we want to determine whether a certain vector is a multiple of another vector, except we have to do this by vector division. So, for example, let's say we want to determine what the legal moves of the queen are. Then the queen can basically move from here to here, or here to here, or here to here. And then let's say if we had a bishop as well. So if we want to determine whether a bishop can move in the same line as the queen can, then we perform a vector division between the vector difference of both of those squares, okay? So for example, let's say this bishop and this queen. this bishop would be located on 0, 2, the coordinates, and this queen would be located on row 4 and column 6, so 4, 6. If we did a vector subtraction of these two, we basically get 4, 4. And then the bishop, one of its legal vector moves is 1, 1, since the bishop can move diagonally. So then 4, 4 is divisible by 1, 1 4 times. So that way we know that the bishop can indeed attack the queen in this particular move. So that's how the vectors are very, very useful in basically representing the different coordinates inside the game. So now we go into this Venn string notation. So I explained it a bit in the last video. Excuse me. So if you're familiar with this, just feel free to skip ahead a few minutes. But if you're not, the Venn string notation is basically how we basically represent each unique board configuration. So this is basically how we can tell the computer which position we are currently in. And you might ask, well, why don't we use an array of 8 by 8 numbers to represent this? So you could do this, but that's how the computer internally stores it. But then if we wanted to basically tell the computer which position we're currently in, we wouldn't use the 8 by 8 since that's basically too much data. It's not very compact. But the Venn string is way more compact and way representing the same information. So this is basically the code of how we do it, but before, let me just show you an example of a Venn string. So this over here is basically a Venn string, and what it represents is each number, each letter represents the piece. So R corresponds to rook, B corresponds to bishop, queen, Q, and etc. The only ambiguity is with knight and king, since they both start with K. But then the workaround here is that the knight, we can represent that with an N, and K with king with a K. And we represent all the black pieces with a lowercase character, and all the white pieces with an uppercase character. And then if we want to represent gaps in the positions, we'd basically represent it with 8. So 8 means there are 8 gaps, but then if there were only 4 gaps, we would do 4, and then we would have the piece. So and each slash is basically it represents it going to the next line. So that's an example of a Venn string. So what this Venn string function does is it basically, given a certain Venn string, it converts that particular Venn string into the 8 by 8 array. So what this does is while the index is less than the length of the input, so the length of the input is basically 8, while the index is less than that, then it will check first of all, if the index is alphanumeric. So it's just alphabetic. So this means that it will basically be a piece. If it is a piece, then this bit of code just determines which piece it is. And the way we do this is num equals 8 if it's upper, else it's 0. So this basically determines the color. And I'll quickly explain how we represent each of the pieces using numbers in just a second. And then this piece of code just translates the piece letter into an actual number, and then it ORs it. So the OR operation, bitwise OR operation, and then it uses this to represent it inside the grid. If it's numeric, then we basically just extend the counter by however many whatever the value of the number is, basically. And then otherwise, we increment the value of the row to the next one, so then we iterate through each row. Okay. So and now just going over quickly how each of the pieces are internally stored. So basically, how this works is, maybe this isn't the best place to show it, but how it works is each of the pieces have their own unique representation. So a pawn is represented with the number 1, and then bishop's represented with 2, and then knight's represented with 3, etc. They're basically an ascending value. And finally we get to queen represented with 5, and king represented with 6. So that's how each of the numbers are represented. But you might be asking, how do we differentiate between a black bishop or a white bishop? And the way we do this is we use the 4th bit. So if you think about it, then the pieces occupy the first 3 bits. We can represent each piece uniquely with the first 3 bits, since there are 6 pieces, and the first 3 bits cover 8 different possible combinations. So since 8 is greater than 6, we can represent all the pieces with using the first 3 bits of any number. But the fourth bit will tell us whether the piece is white or black. So if that fourth bit is set to 0, then we know that it's black. If that fourth bit is set to 1, then then we know the piece is white. So this provides a very neat way of representing whether each piece is white or black, as well as the numerical value of the piece. So from that, we can basically uniquely identify each piece, and that's pretty much it for that particular section. Now we go on to the next couple of functions within this larger foundation functions. So we have this read move. So what this read move does is it basically reads certain input move by the user. So the reason why this is there is this is basically this is more of a debugging tool. So in case you want to actually display the board, there's several different board configurations. You can't use Pygame's nice little compact board representation. Instead, we need to just output exactly what the computer's thinking in an 8x8 array. And if we want to input a certain move, then we use this read move function. This is kind of just a debugging measure, so I won't go into too much depth, but feel free to read about it over here inside the code. If you have any questions, ask me in the comments. Yes, I'll go into the next two functions now. So this is basically the this is a function which converts alphanumeric to coordinates and vice versa. So what this does is we've covered how the engine basically represents each of the coordinates using an 8x8 coordinate system. But then that's not how we think of the coordinates, right? We think of them as squares, basically. Because, for example, if we look at the queen square, in classical chess format, it's basically, that square is G4, since the columns basically go A over here, B over here, C over here, etc. So it would be G over here. And then the rows go 1, 2, 3, 4. So then this particular square would be row G and column 4. So it would be represented by G4. So we need some sort of way to go from G4, which is our human perception, to the computer perception, which is basically row 4 and column 6. So that particular function will be the alnum to coordinates, and then coordinates to alnum. Both of these use ASCII representations, and it's just a very useful tool to convert between the two, in case we need to print the coordinates during any debugging procedures. And then we also have this output function. So what this output function does is it basically just outputs the certain board configuration, and this basically converts each of the numerical formats into its piece. So num to piece, we use this num to piece array inside the initialization function, and then we AND it with 7. Since remember, the piece is basically determined by whether the whatever the first 3 bits are, and then if the fourth bit is set versus not set, then we basically make it lowercase versus uppercase. That basically determines whether which color the piece is actually is. So and then finally we have the move function. So this move function, again, it is more of a debugging procedure, but it basically it takes in a certain move, and then sorry, it's not really a debugging procedure. It used to be a very big debugging procedure, but this is very useful internally when we're looking at future moves. So what this does is it basically takes in 2 coordinates, P1 and P2, and then it takes the grid copy. The grid copy is whatever grid the pieces are currently on, and then it basically moves the piece from coordinate P1 to P2. And the way it does this is it basically sets the original coordinate to 0, and then it sets the new one to whatever that color is. This over here, this is basically just accounting for promotion, since we basically auto-promote to a queen, since like in most cases we'll auto-promote to a queen. We have a very few cases where we actually won't promote to a queen, but more on that later. And then this bit of code basically, if the piece, if the second coordinate is basically there's already a piece on it, i.e. we're capturing a piece inside a move, then we basically need to remove that piece from the piece locations of the opponent's moves, of the opponent's pieces. Sorry. So this piece locations array basically stores all the piece locations of both the current player and the opponent player. And then we remove that particular piece from it. And if the number is 6, then we also update the king locations. Now, all of this might not make that much sense at the moment, but trust me, when we use these functions later on, you will truly appreciate why each of them have a very pivotal place inside our particular engine. So that's pretty much it for this particular video. I really hope you enjoyed watching. Hopefully you learned something new about how each of these functions can contribute to our overall goal of creating a chess engine. And if you enjoyed the video, please be sure to leave a like and subscribe. And if you'd like to, please check out my GitHub as well, where you can access all of this code and play around with it as much as you would like. So yeah, thank you very much for watching. I'll see you in the next video. Bye.